Good morning. Already my colleague, earlier colleague rather, he has given a very updated presentation on what is the kind of simulation will play a role in developing. It's not only specific to automotives, it's generic to all. Now I will highlight, I have not made a colorful presentation, but I'll give you information based on my experience, how we could make good deliveries on vehicle side, because most of my experience was on vehicle development, powertrain development for the vehicles. I'll also highlight how this use of simulation tools help us in reducing the timeline, making it cost effective. These are all the aspects which I'll try to highlight. Now, in the model-based simulations, there are pros and cons. Already Mr. Anand has highlighted very well. We can't totally depend on simulations unless until you have a verified, validated data for aggregates and systems. So there is a need for synergistically working with the aggregate development team and also validating it and using these test results as a feedback. Most of you know that the failure rates is due to the transients. When you integrate motor controller, there are transients. When you integrate battery pack with the vehicle, there is a transients. When you integrate transmission system with the motor, there is a transients. These are all information is missing in the modeling simulations. That is where their need for upgrading the models and making it suitable and using it as a model input for simulations is very essential. Another point Mr. Anand was highlighting, thermal engineering of the systems is very relevant. In India, we have a temperature of minus 10 degree also, we have a temperature of 50 degree also, ambient temperature. So we are the one having a wide range of temperature we need to deal with. So that means our thermal management system has to be so robust. So let's not get into detail now. Let's move on. So I am going to highlight how does that simulation helps us in preparation of architecture, then system engineering, then plant modeling, controller development, verification validation, and finally ending up with the development of vehicles. Here, one of the critical aspect is we can adopt multi-layered view. For example, in the model-based simulations, what we can do, we can find out what are the system requirements. For example, when you go for a fuel cell electric vehicle, you have a hydrogen storage system, hydrogen regulation system, fuel cell system. Fuel cell system comprises of fuel cell stack, balance of power plant, electric traction system, thermal management system, all on vehicle chassis system. All these systems has to be integrated and it has to be made working in synergistic manner. See, what is the challenges here? It's all multi-domain. There is a mechanical engineering is there, electrical engineering is there, electronics engineering is there, control engineering is there, and then battery engineering is there. So all of them has to work together. See, when you start in the automotive industry, mostly earlier it was engines, transmission, engine management system. But now, in contrary, now in the new vehicle technology, it's going to be starting with electrochemistry. Nobody would have thought that 10 years before, chemists will have a role to play, critical role to play. Today it is a need of an hour. So now, when you start mechanical engineer, when he sees chemistry equations, double layer capacitance or conductivity resistance, he really gets jittery about that. When chemical engineer looks at mechanical engineering parts, he becomes very annoyed, and then bringing synergy between them is going to be a really challenging task. That is where this modeling simulation helps. See, as a chemist, suppose I need not understand basics of electrical electronics, but I can use the interface blocks of models and I can configure it, I can do a simulation. See, that is where the simulation model-based system engineering helps in making the people to work synergistically even though they lack fundamental knowledge. That is what the the idea which brings here, it makes design team to make stronger. We can do, for example, system sizing and analyzing the systems. For example, I want to do a powertrain development for the 19-tonner fuel cell bus. See, I can have a system from say X company or Y company, but I want to explore whether which system is suitable, which system will be more performance wise will be better, which can take care of all the transient requirements, which is more energy efficient. When I want to do, then really if we imagine I'm going for a prototyping route and making the vehicles and comparing the vehicles, it will be a huge investment to be made on prototyping, procuring a components, and man hours required to be spent, and then timeline will not be able to meet the timeline also. These are all issues which we will be facing. Instead, if we have a models, we keep it as an input, parameterize inputs, and then start simulating it. Within a day or two, we will be in a position to make a decision on the powertrain configuration, powertrain sizing. That is a kind of timeline we will be able to meet. This is the advantage of using simulations and modeling and simulation we'll have. But otherwise, imagine, suppose you are making a one vehicle means nobody will agree. So at least you have to make 5-6 vehicles, 2 systems you are going to test it, 20 vehicles you have to make. And then associated manpower costs, associated prototyping costs, lead time, all this will have an impact on the project timeline and will have an impact on the cost. But whereas if you are using a simulation tool for making a decision on the powertrain sizing, is going to reduce your time and is going to save your money, and you need not spend the money on prototyping also. See, earlier my experience, I have seen minimum 60 months, 5 years of time from starting from the drawing board to the final vehicle to the field, it will take. But today there is a need for making it happen within 24 months. You don't believe, I think Mr. Anand also will agree with me, because I worked with him, I faced a lot of pressure. That's where I use a modeling simulation tools, we made it happen. So what I am trying to highlight is, need of time is very short, we have to make it happen, we have to exploit the market. That's where these simulation tools helps us in making the product reliable, robust product with a shorter time. See, that robustness doesn't come just because of modeling simulation. Already he has highlighted which are all areas modeling simulation can help us. So I not dwell on this slide. So I'll move on to V&V. See, now logically people, simple V&V they say, it's not simple V&V. For example, you take an electric vehicle. So you have a battery system, you have a traction system, you have power electronic system, you have a mechanical chassis system, and then you have instrument cluster, you have a communication, you have an onboard charging system. All these going to be there as a systems. So now we need to deal with systems of systems. So when you deal with a system, every system has 5-6 components, 5-6 aggregates. Then the right strategy is to have a multi-layered V. See, for example, you take a electric vehicle, you take a battery pack. So battery pack comprises of cell modules, battery pack, thermal management system, then you got a BMS, slave BMS, master BMS, then controller inside. So this itself there is several layers. Each layer you split it up, do a modeling simulation, and then try to integrate it. It makes life easier. We can address to all the related issues. You can address to the material issues, you can address to the controller issues, you can address to the transient issues, you can address to the electrochemical issues, you can address to the mechanical mounting issues. All these issues can be resolved, and then we can go for simulation, and then we can validate, verify, and then we can have a reliable, robust product. So likewise, all the system. For example, you take an electric traction system. Electric traction system comprises of motor, motor control unit, transmission. So then we can take all these things, mechanical related we can address to it, electrical related we can address to it, power electronics related we can address to it, and then material related we can address to it, thermal engineering related we can address to it. So we can have a multi-layered, and then we can address to those issues. We can split it up. The technology expertise knowledge people can work on focused way, and then synergistically weekly once one meeting we can know, okay, you are taken care of all this fine, okay, where we have a synergy or not. See, that is where modeling simulation helps. So planning, system of system, system engineering, and then multi-layered V, and then integration, aggregate level integration, making systems integrating, making the vehicle, then testing. So that way we can plan, we can execute, then expertise knowledge people can be made to work independently without having any clash in that interest. So this way we can manage the project also, we can meet the timeline also, then whatever the shortcomings are there on the modeling simulation side can be covered. So that is the kind of approach will be help us. So there should be a synergistic way of aligning the modeling simulation usage of tools with the systems of system engineering. V&V will be very useful. This is the kind of approach we can adopt for ensuring that the product is robust and reliable. So now system requirements, we can see that we can specify the system sizing, system design. So we take an electric vehicle, what is the kind of battery pack design, traction system design. So we can split it up. So based on the requirements, we fix the boundary condition, and then we can specify each aggregate how it has to perform. So boundary condition is fixed. And then component design, then system integration. That's a V&V cycle, just I'm trying to highlight here. See, we can see here, Gamma Technologies offers tools for meeting all these areas where it can be used in the design and development. And also, see, for example, when you are going for a controller development, you can make a plant model. If you are able to capture all the transient things, so you can use it as a plant, you can make a controller, you can simulate it by simulation tool model or model in loop method or HAL method. Then you can find out whether is there any controller, is there any logical issues are there. We can figure it out. We can debug it in the lab itself. We need not go to the vehicle for debugging it. And then it's also useful. For example, if you have a transient data also there, thermal engineering also we can focus on. Then reduced order model is another concept which can be used as a plan model. We can simulate, even we can find out what is the kind of impact it will have on a various ambient temperature. So we need not go take the vehicle Jaisalmer and test it at 50-degree ambient. We can do a simulation here. We can predict what is the kind of temperature raise will be there during peak summer at various locations, and design optimization also can be done. So what indirectly I am trying to say is that there should be a collaborative way of working with the aggregate designers, get the data, use it as an input and simulate it, extrapolate it. That is where the gap, when you are extrapolating, what is the kind of deviation will be there, that is where the experience will tell us. So there is a continuous improvement has to happen on the modeling and the simulation side also, how the models are improved, how the other parameters are taken care. This is an area where I think most of the aggregate manufacturers or developers, designers, manufacturers, vehicle integrators has to work together to make it happen so that we end up in a reliable, robust product for our customers. Here, GT Suite is one of the examples where fuel economy, energy management. I will not use a fuel economy is a IC engine terminology. Energy management can be done. Fuel economy for hydrogen fuel cell vehicles is applicable. So we can find out with this fuel quantity what is the kind of range for various dry cycle can be assessed. So this is, if we are going for a testing, then it will take long time. But before designing the vehicle, integrating the vehicle itself, roughly we can have an idea whether it is acceptable to the customers or not. We can assess and then we can find out. Vehicle performance overall can be done. For example, modeling simulation can be used as a tool for assessing the range. Also, what is the kind of energy recovery possible at various dry cycles. It also can be used as an input for modeling simulation. And modeling simulation also can be used for HAL validation. For example, we want to integrate all the powertrain components, and then we want to check whether it is going to communicate as per our intention. So we can make a models, we can generate an input, give it as an input to that, and then we can take the output and then we can decode it. We can compare what we expect and what is the response is coming out of the powertrain. Is it in line? If it is not in line, what is required to be done on the controller side? Now imagine we are going for deploying prognostics. All the simulation can be done and can be assessed whether the SOC control algorithm, what we are getting out of the battery going to be there, how the battery degradation going to happen, all this also can be predicted by using a modeling simulation tools. So what I'm trying to say is, all the future technology we are going to use, whether power electronic design, verification, validation, powertrain integration, system integration, or even deploying prognostics, there's a role for modeling and simulation. So that will be the tool which will be using it. That is a kind of future scenario we can look at it. See, for example, when you have a powertrain, we have sized it. Suppose you want to know for various drive cycle, suppose you want to export the vehicle to Europe or US. So what is the kind of drive cycle you have, how this vehicle will behave. For meeting the requirements, what is the kind of design alteration we need to do. That's itself we can do. So the product planning, it will help us in product planning also. So already there are highlights there. So what we need to do is, I already explained this plant modeling, controller development, model in loop simulation, simulation in loop, hardware loop. So all these advanced technologies along with the modeling simulation, if you could use, it will reduce the development time, it will reduce the cost. So that is what I can highlight this. See, now the need of power is, we need to deliver quality. We cannot compromise. And we could have seen many two-wheelers are all going into the flames. It's because improper engineering. There is no proper BMS. There is no proper monitoring of SOC and temperature. And there is no sharing of information. What is the kind of charge rate it can accept during charging and discharging and regen. These are all limitations are there. If we don't do proper engineering, then electric vehicles will have to face a problem. But if we are taking care of this, we will not have a problem. That is where modeling simulation helps. So it's not only shortening the development time, it also ensures the safety of the people on road, on the passengers also. Time is very critical. After 6 months, what the kind of products will be there in the market, nobody knows. It's a very competitive environment. So to cope up with, we have to make it shorter. Cost. So we cannot invest 200 crores, 300 crores for making a vehicles and pass on the burden to customers. So we have to make it cost effective. We have to make it ourselves, and we have to do a validation. We have to use advanced tools, HAL simulation tools, test bench tools, and make it faster and offer a quality product. So that is what, but nothing is 100%. There is always scope is there. So we have to keep learning and try to keep improving. If it is improving on the software side, we can do. But if it is on the hardware side, it is going to be, it will have a dramatic deleterious impact. So we have to ensure that the product is robust mechanically. But software side, energy efficiency can be improved, or BMS can be improved, not compromising on the safety. So this is what the points I try to highlight. By use of simulation tools, we can shorten the time, we can offer the reliable, robust product.